Percent salinity of the ocean, Cody. What's the percent salinity of the ocean? Let's do some percents here. What do you think it is? What do you think the percent of salt is in the ocean?
Oh, 95.9.
Nine. So we got A.
No, I'm just kidding. Don't put that down. Don't.
73.8.
73.8.
58.2.
58.2.
It's more than half. I know that.
75.
75.
8.5. Yeah.
So now we're talking like salt to water. Yeah, the percent of salt in water. You're saying 78?
Yeah. I know it's not over 80. He doesn't write that down.
And we'll do one more. Have we said everybody?
Two.
2%?
Yeah, no.
She's got some highs, we got some lows. All right, so
Make sure you're not throwing some vapor out. Individual substances are distinct. Two types of heterogeneous mixtures are suspension and solutes. Suspension is a mixture containing particles that settle out of it if left unstirred. The muddy water shown in figure 14.1 is a suspension. Pouring a liquid suspension through a filter will also separate out the suspended particles.
very good.
For example, toothpaste is thixotropic. It acts as a liquid when it is squeezed from the tube, but as a solid when it sits on the brush. Some paints are thixotropic. You can stir them in the paint can, yet they don't flow down a stirring stick or brush when you hold them. Solvents must be aware that some clays are thixotropic. These clays form liquids in response to the agitation of an earthquake, which causes structures built into collapse.
Okay, so what's a good example of a thixotropic mixture? Toothpaste. How can you describe the concentration of a solution? So we're going to look at percent by weight, percent by volume, but first we're going to look at the most common one in chemistry, and that's going to be molar. And it says, how do you calculate the molarity of a solution? Anybody know? So it's basically, the concentration of a solution is a measure of the amount of solute that is dissolved in a given quantity of solvent. So what's the solvent? Anybody know? Anybody know what the universal solvent is? Yeah, water. You might want to write that down. Water is the universal solvent. It does the dissolving. It breaks things down. So it says a solution that contains a relatively small amount of solute is a dilute solution. That would make sense, right? A relatively small amount. And then a concentrated solution contains a lot. So molarity, this is the one we use most in chemistry, molarity. It's a capital M for molarity. And it's the number of moles of solute dissolved in 1 liter of solution. That solution is typically water. I'm going to write that down. Usually it is water. Water dissolves most things. It breaks it apart. If you try to do other things, it just doesn't separate very well, and then you have a solid at the bottom, and you just can't react that way. We want reactions to go to completion so we can sell those products and make money. So most chemistry is done in water because it separates the ions, and then the ions can react. So most chemistry is water chemistry. The 0.5 molar solution says add 0.5 mole of solute to a 1 liter volumetric flask, half filled with distilled water. So how would I do that with salt? Anybody know how to do it with salt? So I go to the periodic table, right? And I'm going to find sodium. I'm going to find chlorine. So sodium is 23, chlorine is 35. I add those together, I get 58 grams per mole. That's the molar concentration for sodium chloride. So if I wanted a 1 mole, I would take 58 grams and put it in a liter of water. So everybody see that? They don't want 1 mole, so I'm going to multiply this times 0.5, or half. So it's half of 58. Half of 58, 25, and plus 4 is what? 29. So it should be 29, right? So if you took 29 grams of NaCl, put it in a liter of solution, you would have a 0.5 molar solution of sodium chloride. So it's really pretty simple. If you understand the periodic table and the masses, those are for 1 mole. All you have to do then is just multiply it times what you want. It's a really simple idea. They're not trying to make it complicated because we want you to make money. A percent by mass solution. There's 2 ways you can make the percent by mass solution. You can measure out 3.5 grams of table salt. 3.5 grams, that's the salinity of ocean. 3.5 grams per liter. And you can put that into your beaker and you can fill it up to 1,000 milliliters. Or you can do it by weight, right? So if you were going to, the ocean would be, this would be 100 milliliters because water has a density of 1. So that would be out of 100. You put 3.5 in. So if you were doing this and you were making a liter, then you would need 35 grams. 35 grams per liter would be the amount of salt in ocean water.
It seems so low.
3.5%.
Yeah.
So you can take 3.5 grams, put it in your beaker, and then you can add it to the 100 milliliter mark. That's typically what I do. Or you can take 100 minus 3.5, right? And that's going to give you 96.5, right? And you can measure out 96.5 liters, milliliters of water and then pour it in there. That's typically not what is done. Typically, you just take the mass, put it in the beaker, fill it to the 100 milliliter mark. Then you have a 3.5. That's the easiest way to do it, which is what everybody does. Now, if you're going to do it the other way, that's fine. I'm just telling you, most people aren't going to do it that way. They just take the easy route, put it in there, 3.5, bam. You have a, if you did this to the 100 milliliter mark, 3.5 divided by 100 equals 0.035 times 100 is going to give you 3.5%. Does everybody see by mass? That's how we're doing this. You have a 3.5 grams. We know water has a density of 1. That is 1 gram of water is equal to 1 milliliter. Any question on that? So 1 milliliter of water weighs 1 gram. 5% solution, right? You would probably make more of it. you'd probably make 100 milliliters of it and then just use what you needed and store it on the shelf for a month or two, then throw it away. It's the AC. So we typically make more than we need. Okay, so by volume, step one, we're going to determine the percent of the stock solution. So the ethanol right here is going to be 95%. That's step one. We want to go to 78%. You cannot increase the concentration. Next, you're going to determine how much solution is needed. Lab calls for 100 milliliters. So we're going to take our 95% stock solution and multiply it times 2 because 95 is not 100. That gives us 190, so you're going to make 90 extra milliliters. This is our stop volume. On your Erlenmeyer flash, you're going to stop at the 190 milliliter mark when you're adding the water. So we take our percent that we desire, 78 times 2, that's 156. That's the amount of the ethanol, 95% we're going to measure out. So we measure out 156 milliliters of that. Once we get 156 milliliters, we're going to add water and stop at the 190 milliliter mark. And then we have 190 milliliters of 78% ethanol solution. It works. Quantity of ocean water. Anybody know the percent of salt? 6%. Anybody else got a percent? Got a 6, 5.
How about 4?
4, 5, 6, 3,
Let's go hard. Let's go 8.
and then 8. That's actually pretty good. Pretty good. So we'll talk about that.
As clear as solutions. Dilute colloids appear to be homogeneous solutions because of their dispersed particles are
3.5 grams, put it in a flask. I've drawn a beaker here, but it's typically a flask. And you fill it to the 100 milliliter mark, and you've got a 3.5% solution. Also, the book shows you on page 481 the mass of the solute, which would be the salt, divided by the mass of the solution. So typically that's going to equal 100 grams. That's the objective. So 3.6 divided by 103 gives you a 3.5% solution. But that's typically how we do it, like I've shown you on the board. I don't really like how they've done it here. They're trying to make, it doesn't say here, but this is how we typically do it on the board. If you want a 3.5% solution, you put it in there, fill it to 100, and you have 3.5%. Some places where we have clay soils, and that's why it'd be a good idea for you to have earthquake insurance in case there's an earthquake, because the clay soil could liquefy, causing your house to be damaged.
Size particles between atomic scale size of solution particles and the size of suspension particles is a colloid. Colloid particles are between 1 nm and 1,000 nm in diameter and do not sail around. Milk is a colloid. The components of
particles of the dispersion medium with the dispersed particles. These collisions help to prevent the colloid particles from settling out of the mixture.
Ratios. Which one is the most commonly used one in the lab? Molarity, yes, that is the most common one. Very good, Lily. The molarity of the ocean is close to 0.5. If you look at the percent, it's around 3.5%. Well, that means it's around 35 grams per liter. Would be 3.5%. So this is 29 grams at around 0.5 molar. So it's going to be a little bit larger than that, maybe 0.55 molar. That is the ocean. But we don't talk about the molarity of the ocean because people aren't familiar with it. People have seen percents before, so if you were to say like 0.55 for the molarity of the ocean, they'd be like, I don't understand what you're talking about. But the mole is the most important thing from a scientific perspective because it tells us the number of the atoms, the number of the sodium and the chlorine ions floating around in the water.
Two types of heterogeneous mixtures are suspensions and colloids.
Very good. So let's read about the thixotropic mixtures. Who wants to read there? At there. So the federal government, state governments set standards limiting the amount of contaminants allowed in drinking water. So how much lead does the federal government allow in your drinking water? 0.8? How much lead does the federal government allow in your drinking water? 0. They have a 0 tolerance for lead. No lead is allowed in your drinking water. Salinity of the ocean? Now, if you think it's not listed up there, you can give me what you think. I just wrote up here what other people think the salinity of the ocean is. 7%? 75%? Anybody else? How about Maddie?
What if you were close?
Maddie, what do you think the percent of the ocean is of salt in the water?
85%.
85% salt?
Yes. Was I right?
Well, I'm not going to tell you the answer yet. I just want to know what you think the percentages are.
Wait, what was the question?
Hold them up. Builders in earthquake zones must be aware that some clays are thixotropic. These clays form liquids in response to the agitation of an earthquake, which causes structures built on them to collapse.
Right, so we live in an area where we have a lot of clay soil, and that's the reason why I have earthquake insurance on my home. Now, I can't look underneath of it. I don't know for sure, but we have the Madrid fault that's close to us. It's not a lot a year. It's about $50 a year. So it's worth the risk for me in case there is an earthquake if my home were to like fall apart. Because if you have a home and you have money in your home and there's an earthquake and it's destroyed, guess who's going to lose out? Yeah, you. That's why you have...
Solution. A heterogeneous mixture of intermediate-sized particles between atomic scale size of solution particles and the size of suspension particles is a colloid. Colloid particles are between 1 nm and 1,000 nm in diameter and do not settle out milk is a colloid. The component of a homo
water. Ground in motion results from collision of particles of the dispersion medium with the dispersed particles. These collisions help
be like fog and there are lights shining through it. So the fog is creating this Tyndall effect where you can see the particles. It says that the suspensions also exhibit the Tyndall effect, but solutions never exhibit it. So rays of sunlight passing through smoke-filled air, that's basically what you're seeing there in the Tyndall effect. It can be used to determine the amount of colloid particles in suspension. Now, you might see that in a lake or in a river or stream that's close to, let's say, a company that's dumping illegally. And you can then find them for that. Now, if you look on the next page, 479, you'll see types of examples of solution. Now, water is going to fall into that ocean water where it's going to be a homogeneous mixture. But air, you'll see the solvent. What is a solvent? Anybody know? A solvent is typically something that dissolves. Right. So nitrogen is acting as a solvent there. Now, I didn't know that nitrogen had a solvent characteristic. It's not going to separate oxygen into two ions, but I do believe that it probably surrounds it and or holds onto it, oxygen in the nitrogen mixture. So just because it's more, I guess that's the reason why it's considered the solvent in this scenario. Once again, I don't think that it is separating the oxygen molecule. Commonly used in chemistry. Now, when we talk about the percent of salt in the ocean, they don't give it to us in mole, right? They're giving it to us in percent. Why don't they give it to us in mole? Why don't they say the molar concentration of the ocean is 0.55 molar? Because most people don't remember the mole. Like Emma, she's in school and she's like, okay, I'm reading, but I also forgot. So I forgot what the mole is. So people forget. And it's like we don't drive around in kilometers when we're driving. So if you're not using it, you're not going to remember it. People hear about percents, they understand percents.
There are roads in Louisville that have like the kilometer signs on it. Like it's on the Gene, no.
Yeah, on the Snyder.
like when you go to Costco, there's like a sign that it says like next exit 2.3 kilometers.
Right, but people don't use it though.
No.
It's not really used.
And then they're like